Dear students, in this video we are going to study about the LENZ law, the illustrations of LENZ law, and also how the law of conservation of energy is proved by using this LENZ law. Now let us study about LENZ law. A German physicist, Heinrich Lenz, performed a series of experiments on electromagnetic induction and deduced a law to determine the direction of the induced current. And this law is known as Lenz law. Now let us see what is Lenz law, how to define that. Lenz law states that the direction of the induced current is such that it always opposes the cause responsible for its production. Faraday discovered that whenever magnetic flux linked to the coil changes, an electric current is induced in the circuit. Here the flux change is the cause, while the induction of current is the effect. Lenz law says that the effect always opposes the cause. Therefore, the induced current would flow in a direction so that it could oppose the flux change. By incorporating Lenz law into Faraday's law, the equation 4.2 can be written as E is equal to minus d n phi b by dt. This negative sign indicates that the direction of induced EMF is such that it opposes the change in the magnetic flux. So to understand Lenz law, let us consider two illustrations in which we find the direction of the induced current in a circuit. Now the first illustration. For this, let us consider a uniform magnetic field with its field lines perpendicular to the plane of the paper and pointing inwards. These field lines are represented by cross as shown. A rectangular metallic frame like this, ABCD is placed in this magnetic field, and it is placed in a plane which is perpendicular to the field. Now the arm AB is movable so that it can slide towards right or left. If the arm AB slides to our right side, the number of field lines, that is the magnetic flux, passing through the frame ABCD increases. A current is induced in it. As suggested by Lenz law, the induced current opposes this flux increase and it tries to reduce it by producing another magnetic field, which is pointing outwards, that is, opposite to the existing magnetic field. The magnetic lines of this induced field are represented by red colored circles in this figure 4.6b. Here. So, from the direction of the magnetic field thus produced, the direction of the induced current is found to be anti-clockwise by using right-hand thumb rule. The leftward motion of the arm AB decreases the magnetic flux. The induced current this time will produce a magnetic field in the inward direction, that's again red colored crosses, that is in the direction of the existing magnetic field. So that is shown in 4.6c here. Therefore, the flux decrease is opposed by the flow of induced current. From this, it is found that the induced current flows in clockwise direction. Now, in the second illustration, we are using a bar magnet, and let us move that bar magnet towards the solenoid with its north pole pointing the solenoid. That is 4.7b here. So the north pole of the magnet is pointed towards the solenoid, and according to Lenz law, this induced current will flow in such a way that it opposes the movement of the north pole towards the coil, because here the motion of the magnet increases the magnetic flux of the coil, which in turn induces an electric current. Due to this flow of induced current, the coil becomes a magnetic dipole, whose two magnetic poles are on either end of the coil. So, as you know that the cause producing the induced current is the movement of the magnet. So, according to Lenz law, this induced current should flow in such a way that it opposes the movement of the north pole towards the coil. It is possible if the end nearer to the magnet becomes the north pole, as shown in 4.7b here. So then it repels the north pole of the bar magnet and opposes the movement of the magnet. Once the pole ends are known, the direction of induced current could be found by using right-hand thumb rule. When the bar magnet is withdrawn, the nearer end becomes south pole, which attracts the north pole of the bar magnet, opposing the receding motion of the magnet. That is shown in this 4.73 here. Thus, the direction of the induced current can be found from Lenz's law. Now let us see how the energy is conserved in this. The truth of Lenz's law can be established on the basis of the law of conservation of energy. The explanation is as follows. According to Lenz's law, when a magnet is moved either towards or away from a coil, the induced current produced opposes its motion. As a result, there will always be a resisting force on the moving magnet. Work has to be done by some external agency to move the magnet against this resisting force. Here, the mechanical energy of the moving magnet is converted into electrical energy, which in turn gets converted into Joule heat in the coil. That is, energy is converted from one form to another. So, the energy is always conserved. But, on the contrary to Lenz's law, if we assume that the induced current helps the cause responsible for its production. Now, for this, if we push the magnet a little bit towards the coil, the induced current helps the movement of the magnet towards the coil. Then the magnet starts moving towards the coil without any expense of energy. This then becomes a perpetual motion machine. So in practice, there is no such machine is possible. Therefore, the assumption that the induced current helps the cause will be always wrong. Thus, Lenz's law is an excellent example of conservation of energy.
I am Heinrich Lenz. Lenz's law states that the direction of the induced current is such that it always opposes the cause responsible for its production.